Maciej will be talking about this year's Nobel Prize, and there's good reason for that, because he is probably one of the biggest specialists on superconducting devices in Poland. So he's actually an experimentalist, so unlike theorists, he builds actual working devices, maybe used for thermometry, nanoscale, or like he's apparently able to manipulate single vortices in superconducting systems. Right, and so after obtaining master's degree from Warsaw Technical University, he did PhD in Jyväskylä University, after which he spent some time as a postdoc in Quantronics group in Saclay, Paris, that was established by one of the Nobel Prize winners this year. After that, he came back to Institute of Physics, PAN, where he's based in the last 15 years. It's great to have you, Michel, and the floor is yours.
Thank you very much for introduction. Good afternoon, ladies and gentlemen. So today I will talk about this year's Nobel Prize in physics. So we'll try to see how big can be an object still to show quantum effects. So this will be the quantum effects which are usually associated to exist at the atomistic level, at the level of single atoms, of single particles. And we will talk about how much we can scale them up, because this year Nobel Prize was awarded for the discovery of macroscopic quantum mechanical tunneling, and the word macroscopic is the one that we need to underline. So we will really try to see if we can scale the quantum effects which we know to exist at this very low level, at the single atom level. We can see if we can create objects, build them, engineer them. We would then call such objects artificial atoms, and they would possibly exhibit the same effects which we know from the single particle physics. And the second justification for the Nobel Prize was energy quantization in an electric circuit. So this second part of the justification gave with time rise to the discipline which is now known as a quantum electronics. So it's a discipline which uses these artificial atoms, which I will introduce in my talk, to build bigger circuits and present some new functionalities. Nobel Prize was awarded to these three gentlemen. John Clarke is the most known perhaps for development of squids, superconducting quantum interference devices. Michel Devoret at that time was his postdoc in Berkeley, and John Martinis was his senior PhD student. And Michel Devoret, after coming back from his postdoc to France, he founded, together with two other researchers, Christian Urbina and Daniel Estève, Quantronics group. This was one of the first groups in the world which started to use to combine these two words, electronics and quantumness, and they started to create quantum circuits. I had privilege to be in this group for 2 years as a postdoc, and I was kind of continuing research which was initiated then by this 40 years ago by these three researchers. Okay, so can you hear me well, or it's too loud, or? Yes, okay, so this is about the steering of my voice, yes, okay. Yes, now it's better? Okay. So I gave this subtitle to my talk to stress that we'll be on the quest to search for quantum effects at even larger scale. I gave this subtitle, Schrödinger cat gets bigger. And just to remind you this paradox which was first put forward by Schrödinger in his paper from 1935. He considered a big object, living cat, which would be coupled to some poison, dispenser of a poison, and this poison could be dispensed when in reaction to the radioactive to decay of the alpha of some particle during the nuclear decay. So at that time it was known that atoms can live, these radioactive atoms, they can live in the superposition of state before and after decay, because they are as a wave that they be found at the same time in these two places. And then his Gedanken experiment was that let's couple this superposition to this poison dispenser, and then it would mean that the cat could be found in superposition, which would be inherited from the superposition and this atom level. And then with time, people realized that it's not so easy to put, of course, big object. This was presented as a paradox. People then realized that big objects cannot be put into such superposition because they interact with many degrees. They have too many degrees of freedom they interact with environment, and this gives rise to this environmental decoherence. So the wave function describing such cat quickly collapses, and we can find it only in classical state. But anyway, this problem, this paradox, founded the discussion, perhaps the first moment when people started to consider where is the border between classical physics and the quantum physics. So how big can be an object still to describe it with quantum physics? And this is what we'll try to find in my talk today. So we'll define this basic quantum phenomena, which we know from quantum world. This is quantization of energy, perhaps the biggest hallmark of the quantum physics. Then we know that particles can be delocalized at the quantum level. This gives rise to tunneling, and they can be put also in superposition of states. And as a fourth characteristic of this mini world, I put the decay of atoms. So let's go one by one through this. So what we have, we know that electrons, they live on quantized orbitals in atoms. So they can just think about Bohr model, yes. So they can live either in S or P state. And they can change this state due to absorption or emission of a single energy quanta, which is known as a photon, or as a photon, yes? So, and this gives rise to all this spectra, which is observed in the end of 19th century, Balmer series, Lyman series, when we have transition from one energy state to another. So quantization of energy in atoms. Then we have, as a second hallmark of quantum mechanics, we have tunneling. Perhaps the most familiar for experimentalists doing some nanoscience is tunneling of electric charge across a tunneling barrier made of some thin oxide. So this is a single particle tunneling when the energy, when the electron goes from one side to another, but on the way it must overcome the high potential or barrier, which cannot be overcome by classical means. For example, by thermal excitation, it's simply too high. But anyway, it's part of its wave function, leaks through this barrier, and this tiny tail that leaks out through the barrier gives rise to the tunneling event. Another part of another example of tunneling is nuclear fusion in the sun. This is basically here, to give example, I present the beginning of the proton-proton chain. So you know that in the sun, when the two protons, they try to approach each other, they repel each other due to Coulomb forces. But if they are able to find position very close to each other, then they are bind very strongly together, forming deuterium. And this happens only when they are able to overcome the barrier formed on one side by the Coulomb repulsive forces and on the other side by strong nuclear forces. And when they collide, then the such binding can only happen in one event per 10 in the power of 28 collisions. So this is very rare process. This gives rise to the lifetime. I mean, this rate of the binding of protons in our sun gives us the lifetime of our sun, which is well synchronized also with the development on life on Earth. And so if it would be much longer time, then we wouldn't have enough energy from burning fuel in our sun. If it would be too instantaneous burnout in our sun, then we wouldn't have enough time to develop in the human beings. Yes, so this is tunneling, proton-proton chain. And yet another example is decay of radioactive nucleus. Here I gave as an example decay of uranium-238 in deuterium with emission of alpha particle, which is nucleus of helium-4. And in this emission of alpha particle out of the uranium nucleus, alpha particle must again overcome the barrier, tunneling barrier. So this is basically the process which is opposite to the proton-proton fusion in the sun. The half-lifetime for this process is 4.5 billion years, and so we can say this is metastable state, but with very long half-lifetime. So during my talk, we'll see that we'll be able to think about some artificial atoms. We'll be able to find the analogs of decay, of the quantization and tunneling as for these fundamental processes observed in nature. And as a last characterization of the quantum world, I put here quantum superposition. So here you have the ammonia molecule with nitrogen atom either placed below or above the plane defined by hydrogen atoms, and this nitrogen, the eigenstate in which such molecule likes to stay is the one in which the nitrogen atom is simultaneously on both sides of the plane, because then it can minimize its energy. Molecule can minimize energy if the particle can delocalize in space more. The localization leads to lowering of energy. So, and then by going, so it lives in superposition, and then we can, with microwaves, with coherent drive on such molecule, we can make maser, which is microwave amplification by stimulated emission of radiation, which is nicely described in Feynman. But okay, the molecule can live and be put in superposition of these two states. So quantum superposition is one of the also characteristics of the quantum world. But now we are asking following questions. So this was some popular, say, something which we are all physicists here, so you should be well familiar with this basic characteristic of quantum world. But now we are posing following question: can macroscopic objects, so ensembles of many particles, behave in a quantum way? So if as they were a single particle, okay? So can we find something which is big but still show this quantization, which would decay between some states, which would tunnel, and finally which could be put in superposition? If we can find such object, we would call them artificial atoms. So this would be the objects which can be which could be engineered potentially, which could be used for in proposing some new functionalities. And to find this kind of artificial atom, we need to look for a system, macroscopic system, which could be described with a single wave function. This is our first guess. This kind of question like this was put perhaps first by Leggett in his paper in 1978. And then people knew at that time that superconductivity and superfluidity seem to be a good candidates as a system which is described with a single wave function. So because these are collective states. So let's look at superconductivity, how it's described. We recognize, so first we'll start with the plane wave. Here we have the phase, here we have the amplitude of the wave. This wave could well describe a free electron in crystal lattice. But then for each electron, we would find another value of phase, so the phases are not synchronized. But when the metal enters superconducting state, we tell that we have the breaking of symmetry, which means that now not any value of phase is allowed. Phase stops to be a random variable, but all superconducting charge carriers, known as Cooper pairs, they decide to pick up one chosen value of superconducting phase. So now, and that is why we have only this one chosen value. This is symmetry breaking. And we tell that now the whole system is macroscopic coherent state because all Cooper pairs, big volume of them, bulk volume of these Cooper pairs now is described by the same wave function which was characterizing a single electron. So this macroscopic coherence, just think about laser. For laser light, we know that if I know phase of the laser here, I know the phase of the laser a few kilometers away from here also. Yes, this is coherent propagation of radiation. So here is similar. If I take the big volume of superconductor, the phase has the concrete meaning. So the current flowing in superconductor is proportional to the gradient of phase. So if I have uniform current, if I know phase here, I don't know also phase on the other side of the table if it would be made of superconductor. So this is the state in which quantum effects manifest themselves at macroscopic scale. We call it coherent macroscopic state and then it is in solid state. So we have this macroscopic superconducting phase, which is the same for a large number of Cooper pairs. And since it looks like like formally, it looks like the wave function is the same like of single particle. We now ask, can it behave, show the quantumness? Can we see the effects which are characteristic for a single atom? So can we see the quantum phenomena for such macroscopic objects? So in this case, it would be this big volume of Cooper pairs, the big number of electrons. So we have this superconducting wave function which describes collective behavior of many Cooper pairs. So this I told you that the phase now becomes a macroscopic variable. Importantly, in the superconducting condensate, we have energy gap, which separates the ground state of Cooper pairs, superconducting charge carriers, from excited energy levels. So it means that it's not so easy for Cooper pairs to easily interact with environment. So we should we hope to vastly reduce effects of environmental decoherence because our system lives in kind of isolation. It cannot interact with too many degrees of freedom. And this should promote the presence of quantum effects, okay? So if we want to measure an atom, its quantumness, perhaps we put it in some optical trap, in vacuum, then we can address it with laser and see the transition due to photon emission or absorption. And here we are able somehow to put all these Cooper pairs also in isolation, but this is the isolation given us by nature because of formation of the energy gap, which prevents the system from interacting with its environment. So perhaps the most this will be the main hero of my talk today. Perhaps the most studied system in superconducting physics is Tanner-Josephson junction. It consists of superconducting leads, left and right. Each you can think that this is bulk of aluminum with well-defined phase. For left and right part, this is different phase, and it's separated with very thin layer of oxide. So these Cooper pairs, they may tunnel through the barrier from one lead to another. This is single Cooper pair tunneling, which was first theoretically described by Josephson, who predicted that the supercurrent, tunneling current, this is tunneling current, but single Cooper pair tunnel. So this is not kind of synchronized tunneling, but they just randomly tunneled from one lead to another. That it is described by, this is this first Josephson relation, which tells us that the current that flows through this interface is proportional to the sinus of the difference of phase across the junction. And there is second relation which relates the rate of phase changes to voltage. So when we apply voltage to such element, we should see the phase running in time. And when the phase runs in time, we get oscillating current across the junction. For these two predictions, Brian Josephson received Nobel Prize in 1978. Okay, and now we want to see, this Nobel Prize was awarded for showing that Josephson junction is artificial atom. Okay, so here I'm presenting to you the two papers which were explicitly mentioned in the justification for the this year Nobel Prize, both published in Phys.Rev.Lett letters, one following another on the same year, 40 years ago. One is about this macroscopic quantum tunneling. So quantum tunneling, you know what it is, but we will have to explain what is this macroscopic. So perhaps we will somehow, the big number of Cooper pairs will be involved, but it must somehow be different from this single Cooper pair tunneling that I just described on the previous slide. And the second justification was energy level quantization of some energy levels which we'll be able to define in this Josephson junction. So let's try to see how it looks in details. So Josephson junction can be, okay, this is some, we are mainly theoreticians here, so this is maybe not so interesting for you, but okay, very fast digression. This is how we do Josephson junction. We put on silicon chip, we put polymer, we radiate with electrons. Electrons can break polymer into monomers. Then we do development. We remove the monomers, so we get such cave. Then we evaporate material. The metal lands everywhere, but also in this cave. Then in lift-off process, we remove polymer, and we are left with some nanostructure at the top. And if we want to make junction, we do this kind of mask. So you see here is some bar which is suspended above the silicon chip. So the hanging structure above the silicon chip, like you see here. Okay, so this is angle view, and this is how it looks inside. And now what we do, we evaporate from one angle, first evaporation. We oxidize first layer, and then we evaporate from second layer, and we get overlap. So this is first evaporation. This is the second evaporation. And on overlapping these two layers, we get sandwich. So this is one electrode for the Josephson junction. Here is the interface. And when going from here to here, Cooper pairs must go through this tunneling barrier. So the tunneling barrier has geometrically it is a plane here, which also defines capacitance of the junction, which is intrinsic capacitance of the junction. So let's put such junction into circuit. Here is the junction. This is its intrinsic capacitance. If I tell you that junction behaves like an inductor, to get the first familiarity to the first impression, then you should recognize here textbook harmonic oscillator. So we have, it means that if we put charge on capacitor and we let the system go, this charge will, the capacitor will start discharging, the biggest current will start to flow through inductor, then we change the polarity on the capacitor, and then the cycle will be, then the oscillation will be repeated in other direction, so we obtain the LC oscillator basically, meaning that current oscillates here. And now we can probe this oscillator by sending biasing current. So this is our bias current that is set by experimentalist. And what we want to do, we want to measure the IV characteristic of such junction. Here we have IV characteristic, current, and voltage. So you will recognize here the pronounced supercurrent branch, meaning that current flows. You see, for example, this point, current flows, but there is no voltage. So there is no power dissipated on junction. So this here is due to tunneling of single Cooper pairs through the junction, okay, as long as we are on the supercurrent branch. But then when we try to cross some threshold value, which is known as critical current, this I0, junction cannot sustain this high current, and it transits from superconducting to finite voltage state. In this finite voltage state, its behavior is governed by second Josephson relation, and then if we try to bias even to higher voltages, then we will get kind of quasi-normal transport when the charge flow above the gap. But we want to focus at this moment. Look, when we try to approach here this threshold, when we are very close to the moment and at which junction cannot really sustain this supercurrent, we'll be able to put our junction in metastable state, meaning that it may, if we put it here in this state for a short time, it may escape, we call it escape, out of this metastable state to finite voltage state, but it doesn't need to escape. It is a stochastic process. So we will talk about the lifetime or the escape rate for the junction living in this state. So how does it look? We will introduce some mathematical background, and this is also how Nobel winners were thinking about it. We will analyze our circuit in terms of resistively and capacitively shunted junction model. So this is kind of orthodox model used in the superconducting community to analyze Josephson junction circuits. We write first Kirchhoff law for this circuit, okay? We have Ohm's law going through resistor. This is part of this current goes through capacitor, and the novelty for some of you here can be the current that goes through junction. This is first Josephson formula. So we add them up, and now I rewrote this first Kirchhoff law here, and now we add a second Josephson formula which relates voltage to the rate of phase changes. We plug it to our equation, and then when we do some substitutions, we'll get something which should remind you of equation of classical harmonic oscillator. So in the regime of small gamma, sine of gamma is gamma. With zero bias, it would be exactly the harmonic oscillator, okay? So we have equation which describes dynamics of the phase, which looks like harmonic oscillator, but now restoring force here is not as in the Hooke's law, which is k gamma, but it takes a bit, okay, slightly more complicated character. This is conservative force in this potential, so by integrating this force, we can get the potential energy in which phase evolves. This potential consists of cosine, and here we have linear term. So it is in principle tilted cosine function. We call it tilted washboard potential, okay? And now let's plot here this tilted washboard potential, tilted cosinusoid, yes, this is tilted washboard. We plot it as a function of superconducting phase. The conceptual value also of this such presentation, why people like it, because it allows to map the dynamics of superconducting phase on the dynamics of the particle moving in such tilted washboard potential if we just assume that this is a fictitious particle which coordinate described by superconducting phase. So either we can just analyze what happens with this particle as it lives here at this kind of local minimum, okay? So we here, due to some fluctuations, interaction with environment, this particle will be here excited, so it can oscillate forth and back, but at times it can overcome the barrier due to thermal excitation and escape. But by virtue of first Josephson relation, oscillation of phase will mean oscillation of current. Okay, so in principle, it means that we will have the current oscillating on this junction. Okay, so we have in the regime of small oscillations, we have exactly behavior of harmonic oscillator, but we can tilt potential with the bias current. Okay, this is our knob to tilt. This is experimental knob, so we can make this metastable state deeper or shallower. So we can regulate the escape rate. This is the rate, so it tells us how easy it is for a particle to escape from the well. And so we can regulate rate and lifetime, okay? So we can take the description of this lifetime. It's usually done by employing Arrhenius law, which tells that it tells that the escape rate, which is inversely proportional to the lifetime in a metastable state. It tells that this rate is proportional to, we recognize here Boltzmann factor, which compares the height of the barrier to the thermal energy available from environment. Here's some attempt frequency. So you see that the rate depends on how high is the barrier. When it is lower, then the particle will be easier to escape, and it can be made lower by increasing the bias current. And we can, here we can derive all these parameters of which are needed for rate by analyzing the tilted washboard potential. Also, when the temperature is higher, it will be easier to escape for particle, okay? Because then it's more likely to get enough energy to kinetic energy, and then it will escape over. So we want to analyze the process of escape out of the metastable state, but this will mean that we will put, when the particle escapes here, we will put it into motion. So the phase will start running in time, and by virtue of the second Josephson formula, the voltage will develop. So this is, I try to make this analogy between particle and superconducting phase. So how can we measure lifetime? We extract lifetime from the switching probability of the junction. So we will send on the junction many pulses, and in response of each of these pulses, junction will switch, but it doesn't need to switch. And then if you just apply one pulse, it can be 1 microsecond long. This is what I do in my lab. So if you are interested, you can come to my group and I will show you in details how it looks like. But it means that we have this tilted washboard potential. Particle is deeply trapped in the well, but now we tilt it just for 1 microsecond. So we give this time to particle of 1 microsecond to make decision whether it wants to escape or not. And so this is our probing time here. And it can be shown that the probability for particle to escape from this local minimum is given by this formula. You can find it in my paper, gambling with superconducting fluctuations. But how we measure this probability is the experiment completely analogous to the experiment in which we toss a coin to measure the probability of obtaining head. So we have to toss our coin, say 1,000 times, and count how many times we got head. Okay, so I sent 1,000 pulses and I measure how many times junction switched, and then dividing number of times junction switched by total numbers of trials or attempts, I get this probability. And you see when we measure, this such probability. Of course, for low enough currents, we have very stable state. Junction cannot escape. Its escape probability is 0. But when we increase current, we start to have non-zero probability, and then it goes to 1. So of course, more current, more tilt in washboard potential, shallower local minimum in the potential, and the particle can escape more easily. So this is how we can experimental. This was also one of the ways how Nobel winners in one of their experiments characterize the lifetime, how they measure the lifetime of the particle. So this is of the system. So this is analogy. We tell that this is decay of our junction. In literature, we can meet such statement that we analyze decay out of a metastable state. So I would like to bring your attention to this analogy with decaying uranium by emission of alpha particle. That is why this is the first analog, this decay, because mathematically it is, you can apply exactly the same. If you had uranium atom, and when you look at it for time t and put here lifetime, then you would know what is the probability for it to break. So now we will consider junction as classical oscillator. So this means that we have this tilted washboard potential, and you know that for classically, each value of such oscillation is available. Each value of energy is available. So by increasing the oscillation strength, we increase also the energy. So any value of energy is allowed, and this oscillation of the phase here will mean that we have just oscillation of current by virtue of the first Josephson relation. Okay, so we have the current flowing forth and back, and since it's now flowing forth and back, we would like to see whether we can help particle escape from this metastable state by resonantly activating it out of the well. And this is the first experiment which was done by the Nobel winners. It was still not the one which was awarded, but this was kind of prerequisite to do the Nobel. So here we measure the lifetime of the junction as compared to the lifetime. We irradiate our junction with microwaves, and we check how the lifetime is modified compared to situation when junction is not irradiated. So here we have some baseline for lifetime, and then when we irradiate junction with frequencies, different microwave frequencies, we see that we find pronounced resonant peak, which tells that junction respond at a given frequency. This is roughly here 6 gigahertz. So by absorbing microwaves, we can make this particle or the current here oscillating stronger, which finally eventually leads to the enhanced escape, which is observed as the reduction of the lifetime in this metastable state. So this is resonant activation from the 0 voltage state of a current biased Josephson junction, which shows that junction behaves like kind of classical oscillator, which can be resonantly activated. And now we go to our core question. Junction or phase lives, I showed you that it classically it works, but the question that we pose now, since we have here some confining potential, can we imagine a situation in which this phase would be blurred here? So our system would not be described by the single value of the phase, of the superconducting phase, but it would be rather described by the amplitude probability wave, which would give us, which would tell that the system is simultaneously for many values of the superconducting phase, okay? And then such delocalization of the phase would mean that perhaps some of its tail could leak out of the local minimum, and this would give rise to tunneling in the superconducting phase space. And if the wave here is if we think that the superconducting phase is described by the wave, then it should also give rise to the quantization of energy levels in the well. So only some discrete energy levels would be allowed. So this is just, we do some analogy. You see, this is the classical picture, this is quantum picture. If it was the particle, then somehow we could think that we can make this particle quantum by delocalizing it in this well, and then it would have the discrete energy levels. But here we have to delocalize the phase in the well. So this is the kind of the abstract transition that we have to do from the particle to our system. And now look what it means. If we consider quantum harmonic oscillations in real space, you know, this is harmonic oscillator, which has the first, there's ground state first, second excited state. I plotted for each state the probability to find particle in a given state, okay? So here particle is delocalized in space. But now our system is going to be delocalized in superconducting phase. So delocalization of superconducting phase means blurring of macroscopic current flowing through the junction. So it means that we have at the same time, as long as we don't measure it, we have many macroscopic currents flowing through the junction. Junction is in this wave state, yes? This kind of in superposition in many current states at the same time. So this would mean that we have system in which, okay, which would have the quantum behavior. So it's important that we would have, I again underline, it would mean that we have the state in which we have many macroscopic current values flowing at the same time through the junction. So just imagine, at the same time we have 1 or 1.2 microamps. Yes, these are macroscopic currents. That is why we tell about now the manifestation of the macroscopic quantum effects. Quantum effects at macroscopic scale. So, okay, so what we do now, we measure this lifetime as a function of, this is the first experiment presented by Nobel winners, which is measurement of macroscopic quantum tunneling of the zero voltage state. And here what they measure this lifetime. And what is important that when they measure this lifetime or the escape rate, you can find you use this Arrhenius formula, which I presented to analyze it. And you can see that rate is higher when you increase current, which when you apply to the junction, but also it's higher for a given current when you increase temperature. So temperature can be used as a fitting parameter in this Arrhenius formula. And for the higher temperatures, this fitting parameter exactly corresponds to the temperature of the environment, so in which junction lives. But at the lowest temperature, they found kind of saturation of this temperature. So they found that this rate is not anymore temperature dependent. So this was done by, okay, we can formally, instead of putting here the thermodynamical temperature of our system, we can put something which we call escape temperature. And you see that for higher temperature, we see 1-to-1 correspondence. Our escape temperature is exactly as the one expected from thermal activation model, okay? But when we go to lower temperatures, we get this kind of branching out from the classical prediction, meaning that now the escape temperature is higher than the thermodynamic temperature. So this was how the Nobel Prize winners concluded. They concluded it must be some additional process that, because bigger temperature means higher rate, that helps the system to escape, to switch from the superconducting to normal state. And then they interpreted this new escape mechanism as macroscopic quantum tunneling. So this is this macroscopic quantum tunneling. They consider now, okay, that our particle, which is trapped at a local minimum, this is the process which is classically expected. Normal activation factor, here you have temperature on environment, but also there is the second process which allows to escape particle due to this zero point fluctuation, 0 point energy at the bottom of the well. That is why I put here this quantum energy h nu. So what is important now? Our system escapes from here to here, although it has not enough thermal energy to do it. So we tell it's tunneling, but it is not a single particle tunneling, because what it means that our wave function describing this macroscopic wave function describing our system switches from one configuration to another in phase space, although on the way there is the barrier which forbids the classical transition, okay? So let's underline, this is perhaps the most kind of involved, kind of intellectually point of today's presentation, then the next part will be easier. Macroscopic quantum tunneling is not a tunneling of many Cooper pairs simultaneously across a tunneling barrier defined in a real space, okay? So this, of course, it's this first Josephson formula when you have the barrier and the electrons or Cooper pairs can go from one side of the barrier to another. So this is the single tunneling which is expected at this microscopic level. But macroscopic quantum tunneling is kind of quantum jump of a collective state from one configuration between two macroscopic wave functions, so between two configurations, from one wave function to another, although these two configurations are separated by energy barrier which forbids the classical transition. So for MQT to happen, this is abbreviation for macroscopic quantum tunneling, we don't need any charge tunneling through the barrier. It means that the wave function describing the system on one side of the junction just immediately changes from between these two configurations, okay? So here, this supercurrent branch, it is due to tunneling of single Cooper pairs, okay? Here. Because as we increase phase, we get more current. But this switching is escape due to this escape is due to macroscopic quantum tunneling. Okay, and now the second 5 minutes, maybe 10. Yeah, because otherwise I will have problem I will need to. Yes, is it okay? Okay, I will try to be as fast as possible. Okay. Yes, so we have quantized energies so the first is macroscopic quantum tunneling, and the second point is that do we have the quantized energy in this trapping potential? So what would it mean? That you see, do you recognize this tilted washboard potential? And now we are asking if there are levels here, can we address them with microwave photons? Okay, so what we do, we apply the coherent, we just apply 2 gigahertz tone on our junction, and we measure the escape rate out of this metastable state, and we see that when and here we scan the tilt of the barrier, the applied current. So what we do when we tilt the barrier, we open our potential more. This is basically this process. When we open our potential more, the levels, the ground state and first excited state are far away from each other. But when we open potential, we reduce localization we delocalize phase more, so this should bring two levels closer to each other as we open the potential, and we should hit the resonance condition. So when we are on resonance with this microwave photon, we can do this transition, which will be observed as the increase of the escape rate from the state. So because of course when we excite our system from here to here, then it's easier to escape from this state than from that one, because now the system sees the thinner and lower barrier. And also we can do similar transition from first to second state and from second to third. So what you see here is the spectroscopy of the energy levels in the tilted washboard potential, okay? So it shows, just think about the Heisenberg, about the Bohr model when we measure the atomic spectra. So here we have such spectra which shows the existence of quantized energy levels in junction. We can also irradiate junction with another frequencies, and then we will find that the resonant condition hit at the lower values of the irradiating photons. And this is because, again, when we open our potential more, first we meet the resonance as 3.7 gigahertz, but then when we open it more, the levels, they come closer to each other because due to the localization of the bigger localization of the phase. So importantly, we have in these two experiments, we found that the energy levels are quantized in the well, and also the system can escape through this potential barrier. So here, why it's important? Because this type of quantization is the important for operation of superconducting qubits. So here I'm presenting to you the work of John Martinis, some review article in which he showed how you can read out the 0 and 1 state of such qubit. So when the system is in 0 state, it's more difficult to escape, and then you measure for a given probing current the higher value of the lower value of the probability. But if you are able to resonantly activate your system, then it can escape more easily. So then the probability gets higher. So this is the way how you can discriminate between 0 and 1 state, okay? And then we can apply, we can put such junction. It's okay. This is just very briefly to show you how complicated is the circuit. So here we have junction. Here is the capacitor. We can apply the microwave drive, and then through the transmission line from the left side, and we can excite, do this excitation from ground to first excited state, and also here we can send the bias current which probes the junction. And now, when such junctions, since it has the quantized levels, it can be put in this is the proof that it can be put in superposition of this state. So we apply the coherent microwave tone, and this microwave tone allows to change the state of the junction between 0 and 1 in coherent fashion. So here is the probability to find junction in the ground state. And as we apply this tone, it goes coherently from ground to first excited state and back, and again to ground and to excited. So these are called Rabi oscillations, yes, which are the first experiment which are done with any superconducting or qubit. So you should be able to show that your system can be put in quantum superposition, and this is possible with junction. And okay, this is I have two more slides to go. So this is great because we can do the artificial circuits which behave like atoms, and so we can put on this chip, Martinis put 60 quantum bits, superconducting bits, which then on which we could then employ some algorithm. And at that time he claimed when it was 6 years ago that he can beat the performance of classical computing. Then IBM disagreed. But anyway, this was first moment 6 years ago. Then the quantum computation or this quantum manipulation started to claim that they want to beat the classical approaches. And recently, Google published in one month ago a system. They announced system consisting, I think, here of 105 qubits. So this is they are placed in dilution refrigerator connected with microwave line. Each of the line addresses 1 qubit, and yes, and so these are quite big machines requiring low temperatures, and but usually, even if you have many such qubits, few hundreds, only few of them play a role of logical qubits because of the big errors, which are still not. There are still not good enough solutions to overcome them to arrive to a useful commercial machine. This is the last slide. So what I showed you, what I would like you to remember from my talk is that I made this analogy of the quantum world at the atomistic level to the physics of Josephson junction. So I showed you that similarly to the uranium molecule decaying by emission of alpha particle, our Josephson junction can also decay from superconducting to finite voltage state. Importantly, this decay can be tuned with applied current, temperature, magnetic field, which makes it very interesting for sensor application, which is this is what I do in my lab. I can measure temperature with this kind of approach and also magnetic field. I showed you that analog between tunneling. Here I displayed proton-proton chain, but this I showed you that we can also see analogous effect for this big macroscopic object, which is the ensemble of many Cooper pairs, but here it is importantly it is tunneling in the superconducting phase, not in the real space like here. I showed you energy quantization, so think about the Bohr model. Josephson junction also have the same quantization when it lives in this potential. And importantly, we can do coherent manipulation of these levels, which are verified by application of Rabi oscillation. So this basically proves the coherent evolution between energy levels, which is the coherent evolution of the Bloch sphere, and is a basis for a superconducting qubit. That is why the Nobel Prize was awarded, because this initial efforts, experimental efforts, led to the development of huge discipline, which is quantum electronics. Okay, thank you very much.
Thank you, Maciej, for very.
Yes, so I'm sorry if I was talking too long, but I was not sure whether it would. Okay, whether it would. I had feeling that maybe we can do it.
Understanding. Yeah. So yeah, thank you for a very nice talk. We have some time still, I guess, for questions or comments. So just raise your hand in case you want to ask. Krzysiek? I think it's pretty loud.
Yeah, this will be an obvious question. So we have artificial atoms. And what is the advantage or disadvantage if I compare them with the real atoms and, for instance, these quantum computers based on Rydberg atoms? Can you comment on that?
Yes. So the scaling, and so you know, here we work at the Josephson junction can be this is quantum electronics. Rydberg atoms is more the quantum optics. So there you need the laser to address each atoms, which make it quite difficult to think if you want to build such quantum computer consisting of 1,000 atoms. Here, it's not a problem to really build many qubits close to each other. So the biggest difference is the scaling. But of course, you can get the same. You can measure Rabi oscillation here and there. You can put them into entanglement. So fundamental physics is the same. But then from functional point of view, superconducting qubits are now first in the race for obtaining a useful quantum computer because of the scalability. Coherence is bigger in atoms, but the point is that this is always trade-off. How fast you can access them, how strongly you can couple them to operate them, and how coherent are they? So systems which can be put in bigger isolation are also more difficult to address. So it means that the single operation takes much more time. And superconducting qubits are not so well isolated, but you can do very fast operation on them. And in the end, this trade-off is much better for superconducting qubits than for atoms. But yes, if you can put in something in perfect isolation, then it's quantum, but you cannot really connect to it, because then you break all these superpositions, and then your cat is dead then.
Other questions or comments? Okay.
I'm sorry, I missed something. What is this level? 1, 0, what? It's a quantum level of what?
Here?
Yeah, no, just here.
Here?
Yeah.
So these are quantized levels describing the oscillating current on the junction in circuit in harmonic oscillator like this one. Yes, but think about the classical oscillator. We would have the current bouncing forth and back.
Yeah. Mm-hmm.
So now take the quantum analog of this. I mean, so this is quantum harmonic oscillator. So it means that now your current is given with this type of distribution. So and then when you excitation means that it's different distribution of current, but this is the quantum distribution. This is the quantum blurring of the superconductor of the current on the junction. So your system exhibits purely quantum behavior. So in one case your current flowing through the junction is described with one function. When you excite it, is given by another wave function. So this is the point.
So the current, and there should be a commutation relation between them. Current with what? If you have oscillator, you have momentum and coordinate. Then they do not.
Yes. So here I made this analogy. So here is here you have the here is phase and
phase.
And charge. Phase and charge are conjugate variables for quantum electrical circuits, and for the classical, I mean for the oscillations in the quantum oscillations, the real phase is coordinate and momentum.
Okay. Any other question or comment? Okay, Michel.
If I understand correctly, you mentioned states which are superposition of states with different current. But this also means that you have a superposition of different magnetic fields all around your circuit. Doesn't this lead to some kind of strong decoherence?
So yes, this means this, yes, because then of course by virtue of so the system leaves this is the point that what is claimed in this interpretation, that we really have this superposition of macroscopic currents, which at first sounds very strange, because people tell you can make also some loops, and you tell that your system in superposition of being to have current flowing 1 microamp in one direction and 1 microamp in another direction, yes, and then it becomes for many people crazy, yes, because how you can have these two. And then it would mean that it is in superposition of magnetic field being up and down, yes. But this is how this Copenhagen interpretation works here. That is why we talk about this quantum effects at macroscopic scale, yes. And this is why they were awarded the Nobel Prize, because this was also this conceptual step forward.
Let's conclude, because we are already a bit behind time. So thank you, Maciej, again.
Thank you very much.